Hello everyone. So in this video now, I am going to start talking about how can we combine valence bond theory and molecular orbital theory to actually come up with the molecular orbitals of organic molecules. So in this case, what exactly do I mean by combining valence bond theory and molecular orbital theory? So what it means is that to build molecular orbitals, instead of using just atomic orbitals, we will use the orbitals that the atoms are using for bonding, according to valence bond theory. Let me give you an example with methane, which is the simplest example of anorganic molecules that we can have. So here is a molecule of methane, CH4, okay? So the hybridization of the carbon atom is sp3. It's a carbon with 4 single bonds, tetrahedral structure, okay? So for each carbon-hydrogen bond, the carbon is using an sp3 hybrid orbital and the hydrogen is using a 1s according to valence bond theory. Remember, according to valence bond theory, uh, each atom will have its orbitals hybridized before bonding. And the bonding happens through the hybrid orbitals. If we consider then valence bond theory to build a molecular orbital diagram of a molecule, then the reasoning will be the following. Let's focus on just one bond, CH bond, like this one over here. In this CH bond, the sigma bond is happening in between a hybrid sp3 orbital from carbon and a 1s orbital from the hydrogen. Therefore, to build the molecular orbital diagram for this bond, basically we are combining one hybrid orbital from carbon, one atomic orbital from hydrogen that leads to two molecular orbitals. So one and one, two, forming two molecular orbitals, one bonding and one anti-bonding. The bonding molecular orbital is the result of in-phase addition of the hybrid and the 1s orbital, and this would be the shape of that orbital. Okay? Makes total sense. You get these two together, the wave of these two will join forming a much larger orbital. And this is also a sigma orbital because you can see how in between the carbon and hydrogen nucleus there is electron density and is cylindrically symmetrical. The anti-bonding molecular orbital will result from the out-of-phase interaction of the hybrid orbital with a hydrogen atom, with the 1s from the hydrogen. I'm sorry. Now, once we build the molecular orbital diagram, we think how many electrons do we have to place in the diagram. Carbon will be contributing to this bond with one electron and the hydrogen with another electron for a total of 2. Therefore, those 2 electrons will be placed in the bonding molecular orbital, and that's it. So as you can see, according to the molecular orbital diagram, the 2 electrons in this molecular orbital are actually in a sigma bonding molecular orbital, which looks like this, which is also lower in energy as compared to the atomic orbitals that were used in this combination. The entire volume of the molecule. All right. So if there are 4 sigma bonds, for this bond we have 4, and I'm going to write this here. So for this bonding, we will have, okay, in methane, okay, Hydrogen, there are 4 hydrogens, so there are 4 s orbitals from hydrogen and 4 hybrid sp3 orbitals from carbon. That's in the molecule of methane. Okay? Therefore, if we add these two, I'm going to fix this now so you guys can see what I wrote. So if we look at the molecule of methane, we can tell, we can determine here, okay, in methane, carbon is sp3 hybridizes using 4 hybrid sp3 orbitals to bond in with hydrogen. And hydrogens are using 1s orbitals. So there are 4s orbitals from 4 hydrogens and 4 hybrid sp3 orbitals from the carbon. That makes a total of 8. 8 orbitals to be combined will be producing then 8 molecular orbitals. Remember that the number of molecular orbitals equals the number of atomic or hybrid orbitals that are used in the linear combination. So I could say total of 8 molecular orbitals, from where 4 will be bonding, sigma in this case, obviously sigma bonding, and 4 will be sigma anti-bonding. So the 4 bonding will be at the same level here. It's very similar in energy to this one. We're just showing one, but there are total of 4 with 2 electrons each, because the total number of electrons in the molecule is 8, 2 per bond. And there will be 4 empty anti-bonding orbitals up here. So that would be basically the, the molecular orbital diagram for the molecule of methane. Let's see now a slightly more complex problem. Let's look at the molecule of ethane. Okay, so C2H6. Each carbon here, once again, is sp3 hybridized. Okay, both carbons only having single bonds. That's why they are sp3 hybridized tetrahedral structure. If I would like to build the molecular orbital diagram for ethane, first thing I need to know, how many atomic orbitals or orbitals do I have in this molecule? So I would say 6 hydrogens, each one is contributing with 1 s orbital, so I have 6 s orbitals from hydrogen. Then I'm going to look for how many hybrid orbitals, so I have 2 carbons. Each carbon is having 4 sp3 hybrid orbitals. That's a total of 8 hybrid orbitals, sp3 from both carbons. So if we add the s and the sp3, that makes a total of 14 orbitals. Combination of 14 orbitals will lead to 14 sigma molecular orbitals, 7 of them being bonding, very similar in energy, and 7 anti-bonding, also very similar in energy. And now we would only have to fill up the electrons. How many electrons do we have in this molecule? 2 per bonds, 1, so 2 here, 4, 6, 8, 10, 12, 14. Because we have 7 bonding, sigma orbital, 7, I'm going to say here, sorry, sigma bonding. These 14 electrons will be in the 7 sigma bonding molecular orbitals. And the 7 sigma anti-bonding will be empty. Okay, Very similar reasoning to the one we use for methane. So we can expand this reasoning now to molecules having a double bond, like this one over here, ethane, C2H4. Okay, so because there is a double bond, we know that whenever we have a double bond, one bond is sigma and the second one is pi. The pi bond must be through pure p orbitals. Okay, here is the pi bond. Okay, therefore these two carbons will be sp2 hybridized. Trigonal planar, you can see how everything in gray is on the same plane, trigonal planar, 120 degrees angle, and perpendicularly to the plane of the molecule there is a p orbital which is going to have electron density above and below the plane of the molecule. You can see the plane of the molecule right here. So if we want to build the molecular orbitals diagram for the molecule of ethane, first thing first we need to see how many atomic orbitals or hybrid orbitals are we going to combine. We're going to correct this and say orbitals to combine. So we have 4 hydrogens, each one having one s orbital, so 4 s orbitals from hydrogens. Okay. There are also 2 p orbitals from the carbons. Those are the p orbitals used for the pi bond. One from each one, of course. And there is also the hybrid orbitals from both carbons. Each carbon is sp2. They will have then each one 3 sp2 hybrid orbitals for a total of 6 sp2 hybrid orbitals. Three sp2 per from each carbon. So now if we add all these orbitals participating in bonding according to valence bond theory, that will make 4, 2, 6, and 6 here, 12. Okay, a total of 12. Okay, so remember we only combine orbitals that are similar in energy. So we don't mix sigma with pi because pi has much higher energy. Okay, so first let's take care of the sigma bonds. 4s and 6 sp2, that's a total of 10. If we find this 10, we will form 10 sigma molecular orbitals. From those 10 sigma molecular orbitals, 5 will be bonding and 5 will be anti-bonding. I'm going to say 5 bonding, sigma bonding, 5 anti-bonding. In addition to that, we are combining now 2 p orbitals to create 2 pi molecular orbitals, one bonding and one anti-bonding. Okay? So let me show you how it looks like now in the real diagram. Here is the molecule of ethane. Okay? So, first of all, as I said, we have the sigma bonding molecular orbitals. Those are the lowering energy. For the sigma bonding, look at the sigma bonds here according to valence bond theory. And the sigma bonds are, so we have 1, 2, 3, 4, 5 sigma bonds, so that must be 10 orbitals. Those 10 orbitals are 4s from hydrogens and 6 sp2 hybridized from carbon. So if we combine 10, then we will get, as I said before, 10 molecular orbitals. 5 will be bonding and 5 will be anti-bonding. I am placing the bonding sigma down here and the anti-bonding very high up here in energy. Next to the sigma, we will have the pi bonds. Okay, so the pi electrons here, there is one pi bond out of carbon-carbon, each one with one p orbitals. If we combine two p orbitals, we get two molecular orbitals. One pi bonding in phase addition of p orbitals, looking like this, and one pi anti-bonding out of phase addition of the p orbital, looking like this. Okay, and now this would be the diagram here. Okay, so what would be the real how many electrons should we add in this diagram? So we have 2, 4, 5, 6, 10 electrons from sigma bonds and 2 from the pi bond, total of 12 electrons. We will be having 5 sigma bonding molecular orbitals with each one with 2 electrons. So that will make 10. And the remaining 2 will be in this pi bonding molecular orbital. So this could be the molecular orbital diagram for the ethane molecule. Something I want to show here for the first time, if you look at the entire molecular orbital diagram, the higher occupied molecular orbital is this one. So let me write this here. In molecular orbital theory, we call the HOMO, highest occupied molecular orbital, is the molecular orbital that is high in energy and has electrons. In this case, this one here. Okay? And there is also the lowest unoccupied molecular orbital, which is the highest molecular orbital, sorry, the lower energy empty molecular orbital. So lowest unoccupied molecular orbital, in this case, is this one. So as you can see here from this diagram, and again, let's assume we have 10 electrons here, because we do, and then these 2, the electrons that are hiding energy are the ones participating in chemical reactions. Those are the ones farther from the nuclei. In this case, those electrons are in this pi bonding molecular orbital. Okay? Therefore, whenever we see organic molecules with pi bonds, usually in many textbooks, they will only show the molecular orbitals for the pi electrons. The reason for that is because those are the ones higher in energy, those are the ones participating in reactions. But you should also know that below those orbitals, you have the inner molecular orbitals that are all sigma bonding molecular orbital. Something that I also want to emphasize is how high in energy is the sigma anti-bonding. This comes out of a calculation, right? Even higher in energy compared to the pi anti-bonding. Expanding on this idea, now we can go to a triple bond. So for a triple bond, okay, in this particular case, this molecule, any triple bond, 2 bonds will be pi and 1 will be sigma. So let's analyze in theory how many bonding and anti-bonding orbitals should we expect to have in this case. Okay, so I'm going to say here, first of all, orbitals to combine. Okay, so total orbitals to combine. We have 3 sigma bonds, one here, and one here. Okay, so in these 3 sigma bonds, we have 2 hydrogens, so 2s orbitals from hydrogens. And then we have hybrid orbitals. To combine, we have one sp hybridized carbon here, triple bond, and a second sp, so that's a total of 1, 2, 3, 4. 2 sp, each one having two hybrid orbitals, that's a total of 4 sp hybrid orbitals. Okay, 2 from each carbon. That makes a total of 8, sorry, 6 orbitals to combine, okay? 6 orbitals to combine. And in addition to that, and I'm adding this later because we first look at the sigma, now let's look at the pi bonds, okay? So 2 pi bonds, therefore we are having 2 p orbitals for 1 pi bond, look over here, and 90 degrees from there we have another 2 p orbitals for the second pi bond. So we have in addition 4 p orbitals from pi bonds. So if we add all this to create now us combination, the linear combination of these orbitals will lead to, will result in 2s and 4sp, that's a total of 6. 6 orbitals, atomic and hybrid, will form 6 sigma molecular orbitals, 3 bonding and 3 anti-bonding, and 4 p orbitals will lead to 4 pi molecular orbitals, 2 bondings and 2 anti-bondings. Okay? Let me show you now how this looks in a real graph. So this could be the diagram for the ethane molecule. Okay. And let's see if you guys can see the diagram well. Let me fix this graph so you can all see what's going on. Okay. So here is how the molecular orbital will look like. But so we are only showing here one of the sigma orbitals, which is the sigma sp3. I'm sorry, the sigma sp, which is this one. But we have to understand once again that it's a total of 6 orbitals. Okay, 6 sigma orbitals, sigma molecular orbitals. I'm sorry, I had that already written there. So we have a total of 6 sigma molecular orbitals, which we know is they result from the combination of 6 orbitals, 4 hybrid and 2s. So these 6 sigma molecular orbitals, 3 are going to be bonding, so they're going to be a total of 3 over here, including this one, and 3 anti-bonding. And in addition to that, we have 4 pi molecular orbitals. Why? Because we are combining 4 p orbitals from the two double bonds. So remember, if we have two p orbitals on one carbon, another two p orbitals in another carbon, but we can only combine the ones that are properly aligned. So we are going to combine PC and PC. Combining these two leads to two molecular orbitals, one bonding over here and one anti-bonding over here, out of phase, in phase. Combine the py with another py from the other carbon, that's two, leading to two molecular orbitals. One bonding over here, look at the orientation, and one anti-bonding over here, look at the orientation. So combination of 2 and 2 leads to 4, 2 bonding and 2 anti-bonding. Now we think about how many electrons. If we have two pi bonds, each bond has 2 electrons, so a total of 4, 2 and 2. Similar to the reasoning that I did before with ethane, in ethane, the electrons that are hiding energy are, once again, in pi molecular orbitals. So if we want to think about reactivity of this molecule, the electrons that are highly active are the electrons in the pi bonding molecular orbitals coming from the pi bonds. Okay? So we could easily ignore the sigma. You don't need to show the inner electrons. I'm just showing here so you know that they exist. And these electrons in molecular orbitals, the pi electrons, are in two molecular orbitals, one pi z and one pi y, which are equal in energy. So they are called degenerate orbitals, and both are full with 2 electrons each one. So that could be the molecular orbitals of two different functional groups. In this case, a triple bond will look like this. A double bond will look like this. Okay? So with that idea in mind, we can move now to another functional group similar to those two. In this case, we're going to look at a double bond CO, or a carbonyl functional group. What's the difference in between this CO and the CC that we saw before? Well, in this case, we have two different atoms, one of them oxygen being more electronegative. Look at the diagram here. Here is the p orbital once again. Now in this picture, I am only showing the pi bond because, as I said before, the sigma bonds, there are 3 sigma bonds, one here, one here, one here. They will be, the sigma bonding will be below here in energy. We don't care about them anymore. So let's focus on the pi, which are the higher in energy, and those who are participating in reactions. Okay, so in this pi bond in between the carbon and the oxygen, one carbon here, so here is a carbon with a p orbital for the pi bond. Remember, a pi bond, side by side overlapping of pure p orbitals. Here is the p orbital from the carbon, here is from the oxygen. Now, something that is significant here is the leveling energy for the p orbital for the oxygen is lower as compared to the carbon, because the oxygen atom is more electronegative, which means that attracts the electrons more. These electrons are closer to the nucleus, they're lower in energy. That's why whenever you have different atoms in a molecular orbital diagram with different electronegativity, the one that is more electronegative, those orbitals have to be lower in energy. Okay? Now, if we combine two orbitals, two p orbitals, we should get two molecular orbitals, one bonding in phase addition, one anti-bonding out of phase interaction. This is how they will look like. Now, look at this. In this molecular orbital, now the size of these lobes, okay, is not equal anymore. This is a different thing. You never saw this before. The reason for that is whenever you're building molecular orbitals from two different atoms, the resulting molecular orbital will resemble more the closest atomic orbital to it. So, in other words, this bonding molecular orbital is closer in energy to oxygen than to the carbon. Okay, these two are closer. So this orbital resembles more the oxygen. That means that it has a much lower lobe on this side, which basically means that there is much higher electron density over here than over the carbon. Okay. The antibonding is closer in energy to the carbon. Therefore, the lobe is much bigger on the carbon side. So that's the out of phase antibonding. Now we look how many electrons do we have in a pi bond of a carbonyl compound. 2 electrons, so 1 from the carbon, 1 from the oxygen. So we place these 2 electrons in the bonding molecular orbital. So this would be now the summarized molecular orbital diagram for the molecule of acetone for any carbonyl functional group. And I want to say for the first time something that I want you guys to understand. So you can how molecular orbital can predict reactivity and electron density. So here is a carbonyl. Everybody knows from bond polarity according just to valence bond theory. Oxygen is more electronegative than carbon. So these electrons are closer. This is a polar covalent bond, the sigma bond. So the electrons are closer to the oxygen than to the carbon. That means that there is a partial negative charge over the oxygen and there is an electron deficiency over the carbon, okay? That's what it means. Now let's look at the molecular orbital theory diagram. The 2 pi electrons are in these orbitals, and look at the shape. So this orbital is much bigger in the area next to the oxygen. That basically is telling you the same thing. According to molecular orbital theory, there is a much higher electron density over the oxygen as compared as over the carbon. Okay? So next I want to look into the acetate ion. So now this is the next level of complexity. Before we were looking once again 2 atoms, okay, both sp2 hybridized, focusing on the pi bonds, looking at the p orbitals, building the molecular orbital. Now let's look at the acetate. So we have a carbonyl here, sp2 oxygen, sp2 carbon, and there is an oxygen here that you guys know now from Chem 2110 that is also sp2 hybridized. Remember, whenever you have atoms with lone pairs next to a double bond, that atom will be sp2 hybridized as well. So now in this case, we have 3 sp2 atoms next to one another, here, here, here. Because of this, remember, that's how we introduce resonance. I will show a resonance video later. So we have 3 sp2 atoms next to one another. This is a delocalized system. And that's how we use resonance theory to express that on paper. So let's try to make the molecular orbital. So here is the acetate ion. Okay. As I said, if we're going to build the molecular orbitals for the acetate ion, the first thing to understand is how many atomic orbitals are we combining? And we are only focusing on pi bonds, pi electrons. Okay. So the question is, once again, we need to translate it, which is how many sp2 atoms next to one another do we have in the acetate ion? So this oxygen and this carbon are obviously sp2. There is a double bond. And as I said before, atom with lone pairs next to a double bond, that's also sp2 hybridized. So we have 3 sp2 atoms, okay? In this sp2 oxygen, remember, One lone pair is in p orbital, the remaining two are in hybrid sp2 orbitals. So we have a total of 3 p orbitals, one with a lone pair in this oxygen, one here and one here forming this pi bond. So if we have 3 p orbitals, once again, we combine 3 p orbitals, we will get 3 molecular orbitals. Because we have 3 molecular orbitals, we know that the highest number of nodes will be number of molecular orbitals minus 1, 1, 2, 3, 1 is 2, so the highest will have 2 nodes. Below that, 1 node, 0 nodes. So now we know 3 sp2 next to one another, 3 p orbitals. 3 p orbitals, 3 molecular orbitals, 0, 1, 2 nodes. And now we can just build the diagram. Second time I'm repeating this. So if we have no nodes, there is no change in the sign of the wave function. So we basically add. So the resulting molecular orbital will look like this. No, the three, so right here, same phasing, constructive interaction. Right here, same phasing, constructive interaction. Underneath, same phasing, constructive interaction, same phasing, constructive interaction. Zero nodes. Next one, we will have one node. So for one node, it means that it have one disruptive interaction, one change in the sign of the wave function. Nodes in molecular orbitals will always be symmetric, and I said this before. So one node that is symmetric, it must be right in the center. There are 3 points in the orbital, so it must be right in the center to be symmetric. And I am not drawing once again anything in the center because there is a nodal plane here, meaning there is 0 electron density. So we don't draw any orbital there whatsoever. Nothing, 0 electron density. One disruptive interaction on top, the same on bottom, so that's one node. And in the top orbital, molecular orbital, we have 2 nodes, meaning 2 disruptive interactions. So basically the only option here is alternating. Okay. So it will look like this. So one disruptive interaction here and one over here, 2. One nodal plane here, one nodal plane over here. Okay. So as I said before, this is the molecular orbital diagram for any system having 3 sp2 atoms next to one another. Now, to make it particular for the acetate, we need to know how many pi electrons in the acetate ion. So there is a pi bond here, that's 2 electrons, and there is a pi orbital here with another 2, that's a total of 4. So if we have 4 electrons, we add 2 in the first orbital, and we add another 2 in the next orbital. Okay? That's a total of 4. The highest occupied molecular orbital is this one, 2 electrons. The lowest unoccupied molecular orbital will be this one. So I want to emphasize something that I didn't mention before regarding the acetate ion. As you know, because we have 3 sp2 atoms next to one another, that's a condition for delocalization. This is a delocalized system. That's why we're using resonance theory to show that the negative charge is shared in between this oxygen and this oxygen. So basically, in the acetate ion, both oxygens in both ends of the system will be sharing the negative charge, not the carbon, according to resonance theory, valence bond theory. If we looked, so these 2 electrons are sharing between these 2 oxygens. If we look at the molecular orbital diagram. The HOMO is this one. That's where the two electrons that are hiding energy are located. And right here, if you look in the carbon right in the center, there is 0 electron density, and these two electrons are also shared in between the two oxygens, the ones in the end of the p system chain. So that actually shows beautifully how molecular orbital theory and resonance theories, they actually come together and can both explain beautifully the electron distribution of the acetate ion, which is an electron-rich system with the electrons hiding energy being shared in between both oxygens, according to resonance and according to molecular orbital theory. So now we're going to go back to the presentation so the thing doesn't happen again. Oh, sorry. Okay. So here we are in the presentation again. It's the acetate ion, as I mentioned before, same thing that I explained. Sorry for the first time that I was explaining just using this slide, which was fine, but you couldn't see what I was talking about. So hopefully you understood that. And then lastly, I want to show a similar example. So here is a system which we call allylic carbocation. The allylic carbocation is a carbocation because there is a carbon that has a formal charge of +1, positively charged carbon. That's a carbocation. So if we want to build the molecular orbitals for a carbocation, the allylic, we need to think first, okay, how many p orbitals are next to one another in the system? Same question could be, how many sp2 atoms do we have next to one another? We know that these two carbons are sp2 because there is a double bond. And next, there is a carbon, which is a carbocation, and we also know that any carbon with a positive charge is also sp2 hybridized. You're supposed to know this from Chem 10 and 110. So 1, 2, 3 p orbitals next to one another. 1, 2, 3 sp2 carbons. That's the reason for that. 3 sp2 carbon, 3 p orbitals. One is empty, but it's there. So if we linearly combine 3 p orbitals, we get 3 molecular orbitals. One with no nodes, one with one node, and one with two nodes. Exactly as we did for the acetate ion. And now next we need to think how many pi electrons are in the allylic carbocation. There is 2 electrons here in this pi bond, and there is none here because the pi here is empty. It's a carbocation. So the total number is 2, which can be placed in the lowest energy level orbital. So this could be now for the allylic carbocation, this is the HOMO, highest occupied molecular orbital, and the LUMO will be this one. You can see the pictures here much better. So this could be HOMO with no nodes, the LUMO having a node in the center, okay, no electron density, and then the following antibonding orbital. Okay, so one thing once again, and this I'm gonna leave it as homework. We can discuss this on Thursday. So I invite you to draw the resonance structure of the allylic carbocation and explain the structure of the allylic carbocation based on the resonance theory, and then compare to the prediction of molecular orbital theory. Okay. I also would like you guys homework to do this homework, by the way. It's not to be graded or anything. It's just as independent work. You should do also the molecular orbitals for the allylic carbon ion and the allylic radical, both molecular orbitals and resonance structures, and then compare that. Okay. All right. So with that, I'm going to end this video in which we have learned, hopefully, how to build molecular orbitals for organic functional groups. And then we went into an even more complex system in which we have more than 2, so we combine 3. You can also do the same to combine 4 and 5, and we can do that maybe on Thursday. Okay? I apologize for the mistake with not showing the picture of what I was doing, but I repeated it. So hopefully you guys can skip that and then see the whole video. Okay? Well, thank you guys, and I will end this video over here.